Good morning, I am Mr. Ish. If you are watching this video, thank you for doing so. We have a mouthful of a title over here, Extrapolate Very High Order Derivatives. It sounds more complicated than it really is. If hypothetically you had a specific function and you sent it through a derivative, you know you'll get a first order derivative because you've done that derivative procedure once. If however you do the derivative procedure again, you'll end up getting another derivative of this derivative, which now serves as your parental function, and you get a second order derivative. You could technically carry this out a number of times, and then what we are looking here at are high order derivatives. But for functions which are seemingly easy, like polynomials, hypothetically 2x cubed minus 5x, you could do a derivative procedure once and you can get 6x squared minus 5. You can do the procedure again, you'll get 12x. Do the procedure again, you'll get 12, and you can do the procedure one more time, you can get a 0. What you've done is take it through 1, 2, 3, 4 cycles of derivative, and then your original function vanished, it phased out. You cannot do extremely high order derivatives on some functions because they disappear or they get consumed in that procedure. But there are some functions out there where you can keep evaluating extremely high order derivatives, or you can do high order derivative calculation on an unlimited basis, because that specific type of function cycles back and forth relatively between the original function and derivative. Each step it reverses the original or it cycles back, and you can keep taking that to an unlimited number of attempts. In this video we'll be looking at 3 questions from the first to the third, from the easiest to the harder style of question, and I believe you'll find this video to be very beneficial. For our first question, let's just say our function is this, e to the x over 2, and we have to find the derivative. And you know what, we can show you some terminology over here. We have to find a very high order derivative for this function and let that order be to the 22. You're not saying it's d to the power of 22 here, it just means you're finding the 22nd derivative of this function. How you go about these type of questions is very well identified in this word extrapolate. Extrapolate means you're trying to discern some sort of pattern, logical pattern or trend, which you can use to come up with a reasonable outcome which would very likely be true, something which you are predicting to occur down the road. If you were to carry this out through a single derivative, and when you're looking at these type of questions, it's normally beneficial to take it up to 5 levels of derivatives, because then you have enough information to do your discerning or your evaluation or your extrapolation for that outcome that you're looking for. But in some functions you don't have to go that far as number 5, but in some you do. In this one it's relatively easy. Like I said, we're starting with the easy, then we'll go to the harder question. When you take this to the first order derivative, you have to do a chain rule, because you have a bit of a composite derivative with respect to u. You're looking at e to the u, because you were originally thinking u is equal to x over 2, right? U is equal to x over 2. Then you carry that through the chain rule, du or dx, x over 2. When you do this, this comes out as a 1 or 2, and then you have e to the u, you resubstitute it, you get x over 2. So that is the outcome of the first order derivative. Then you take that outcome and you send it through the next round. Here I'm taking the 1 or 2 out as a coefficient, and I'm going to repeat the chain rule, because now I'm really looking at this. Once a 1 or 2 is pushed out, I'm looking at this, which was just like that, e to the u and then du or dx. Remember, here we're employing the chain rule, x over 2. And what do I get? I get a 1 over 2 which multiplies with this 1 over 2. I get a 1 over 4 and then e to the u, but we resubstitute back. So what am I seeing here? In the first round I had a coefficient of 1 or 2. In the second round, second derivative, I had a coefficient of 1 over 4. In the nth round I will have a coefficient of n, right? But I'll always have this x over 2. So if the nth round is my 22nd round, because I'm looking for a derivative, the 22nd derivative, my answer might very well be 1 over 2 to the power of 22 e to the x over 2, and this answer here would have been solved and it would be right. This question is easy because after 2 rounds we are able to determine a pattern. The next 2 questions are not so easy. It may take up to 5 rounds to come up with a good discernible pattern, from which then we will do our extrapolation and come up with that high order derivative end result. Our second question is an interesting one. I've created space here on the board because we will have to do at least 5 rounds of derivatives to come up with a good pattern to handle that. We have a function cosine 2 theta, which is a composite function. We have to find the 103rd order derivative, or what would be the end result if this function were taken through 103 rounds of derivatives. It's a pretty large number. The best way to proceed with this type of question is 5 rounds of derivatives, and you'll have your pattern determined. And do chain rule. If d over du is cosine u and then du over d theta 2 theta, the chain rule elements are here in place. You're going to get a minus 2 sine u, which is just 2 theta. That right there is my end result or outcome from the first derivative. The second one, always push these coefficients out and then do your chain rule. I'm going to look here at a sine u and then du over d theta 2 theta, and then soon a good pattern will start becoming visible to you. You have a minus 2 being multiplied with this, you'll get a minus 4. Derivative of sine u is a cosine u, and we'll put the u substitution back, and that's my second order derivative outcome. Let's go to the third. We'll bring the minus 4 out, and then we're doing d over du cosine u, and then du over d theta. We're doing a 2 theta here, because this right here is a chain rule, all of this, it's not hard. Multiply this with the coefficient, you're getting a minus 8. Derivative of this is a minus sine u, which will make it a positive 8. And then you'll have a sine u, and then you'll have 2 theta. And then let's go to the fourth round. Bring out the coefficient d over du sine u. Again, the chain rule is coming into play here with each step, and each step is relatively similar. 2 times 8, remember derivative of 2 theta is 2. Theta disappears, 2 times 8 is a 16. Derivative of sine u is a cosine u, and we get 2 theta over here. Last round, because it would be prudent to go up to the fifth round, we'll bring the 16 out, d over du cosine u, and then du over d theta 2 theta. 2 times 16, 32. Cosine u comes out as a minus sine u. We'll bring out a minus here, sine u 2 theta. So now let's see what pattern are we getting. These are my end values, the round of derivative or the derivatives round that I'm on. I'm going from a minus, minus, positive, positive, minus, right? Let's get this out of here so we're not confusing the minus. So it seems like we have 2 minuses, then we have a positive. Let's bring a positive here, and then we will have another minus here. We can very well extrapolate. The next step would be, we're going 2, 4, 8, 16, 32. This would be a 64, and this right here would be a cosine, and this here would be a 2 theta. So we have 2 minuses, 2 positive, 2 minuses, so it cycles between that. And it always goes sine, cosine, sine, cosine, sine, cosine, and this is always 2 theta. But the most important factor to look at is right over here. These. Everything is by 2 to the power of n's. 2 to the power of n, right? And then we have to have some function over here, and then we always have 2 theta. How can you determine this? Well, think of this as 1, 2, 3, 4, 5, and 91, 92, 93, 94, 95. 101, 102, 103, 104, 105. This would be my 103. Because here I would get 5, 10, 15, 20, 25, 30, 35. These are my rounds. This will go all the way up to 100. And then this will become 101, 102, 103. Whatever you see over here is what you're going to put right here. I'm going to get a sign over here. My n value now will become 103, right? And that right there will be my answer. 2 to the power of 103 sine 2 theta, and that should be good. That's your this value right over here, the 103rd derivative. So how did we do it? We did 5 rounds, and then each of these rounds just does not represent 1, 2, 3, 4, 5. Ignoring these coefficients, it represents a similar pattern which comes. This could be 1, this could be 11, 21, 31, 41, 51. Going by tens, this can be 12, 22 onward, you know, you get the idea. Because this can be 5, 10, 15, 20, 25, 30, 35, going all the way up to 90, 95, then 100. This becomes 101, 102, 103. And I'm looking for my 103rd, and there it is. I just have to do 2 to the power of 103 and then copy the rest, and we're good. And we already have the signs established. For every 2, they're minus, they're 2 positive, then 2 minus, 2 positive. And that's how you do this. Our third and last question is that function we see right there. Theta sine theta, you see a product of 2 functions. Let that theta, the original theta you're seeing right there, or the initial theta be your f function. Sine theta can be your g function. We're seeing a product of 2 functions. Therefore, we're not looking at the chain rule over here. We're looking at the product rule. And we have to find the 35th derivative. So you can say derivative order number 35. We have to find that. This question has the potential to become messy here, especially on this board. Simply because we have a product rule, and you know the template for the product rule. We have to do at least 5 rounds over here to come up with a good pattern. But I don't want to get lost in this messiness, so we'll have to do some expediting procedures here, or I might have to do some shortcuts here. But we'll see how things play along, and then we'll go from there. When you're looking at that initial function, you're doing the derivative of that, and you're looking at a product rule come into play. The g function times the derivative of the f function plus the f function times the derivative of the g function. If you were to do all of that, we'll do the product rule over here just for the maybe one and the second step, but then after that we'll have to skip steps for that space limitation I was talking about. We'll do the g function times the derivative of the f function plus the f function times the derivative of the g function. This right here in its computation will give you what you're looking for as your outcome of the first. Here you're getting a sine theta plus theta cosine theta, and this right here is the outcome of the first step, which will become the input of the next step, the second step. We're going to be looking at the derivative of this. Now we have a sine theta over here plus theta cosine theta. When you do this, I won't skip step for this step, but I will from number 3 onwards. When you do the derivative of sine theta, you get a cosine theta. When you do the derivative of this, you gotta do the product rule here again. Cosine theta times the derivative of the f function plus the f function times the derivative of the g function. When you do all of that, you have to bring everything together, simplify it, and present a good answer. You'll have cosine theta. Here you'll have plus cosine theta. Derivative of theta is just a 1. Multiplies with that, you get a cosine theta. Minus derivative of cosine theta is a sine theta, which multiplies with that. You get a theta sine theta. Combine all of this. You'll have 2 cosine theta minus theta sine theta. So that's the outcome of the second step. Now, very early on, some pattern is coming into play. Here we have a coefficient of 1, here we have a coefficient of 2, and our end result is always in 2 separate parts. Either there's a positive or there's a minus, and then we have an alternation going on here with regards to these. Either we have a sine or we have a cosine, either we have a cosine or we have a sine. So there are a bunch of things which are going on. In the step 3, you would have to feed that into your derivative, and you'll do 2 cosine theta minus theta sine theta. What I will do now, for neatness sake, is I will do the work here on the side on my notebook, and then from my notebook we'll easily transfer each step answer right over here, and then we'll see if we can develop that pattern. From my third round, when I send this through the product rule and I do this separately, because here we have a polynomial of trigonometric functions, I'm getting this as my outcome. I'm getting a minus 3 sine theta minus theta cosine theta. This is outcome of the third order step, third order derivative, which will now feed into the fourth step, and we will again do exactly what I did right here. I'll do the work here on the side and I'll post an answer. This way everything will be neat. The outcome from the fourth round is giving me a minus 4 cosine theta plus theta sine theta, and we should do one more round, then I believe we would be good. And that outcome will serve as the input of this next round, minus 4 cosine theta plus theta sine theta. And again, I'll do the work on the side and I'll place the answer for you here on the board. As my outcome for this fifth round, I get this. I get a 5 sine theta plus theta cosine theta, and I believe we have enough information now to extrapolate an answer. I'm seeing several things come through, focusing only on this initial part. I'm seeing a 1, 2, 3, 4, 5 as a coefficient. So if we're going to the end value of 35, we'll have a coefficient of 35. That makes sense because we're linearly increasing by value of 1. I'm looking at it round 35. You can also look at this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15, 20, 25, 30, 35th round. So number 5 round will be equivalent to 35 round. Anyhow, we have a 35. Now let's look at the signs. I'm seeing a positive, positive, then I see 2 minuses, then likely the next 6th one would be a positive. So it's always 2 positives, 2 minuses, and then 2 positives, and it cycles. Whatever you see in the 5th round will mirror what you see in the 35th round in terms of the signs. So it'll be a positive. I see a positive here, it should be a positive here. Again, I'll say this is 5, 10, 15, 25, 30, 35. 35th round derivative will mirror your 5th round derivative. What do we see here in terms of your function? Well, if the 35th round mirrors your 5th round, the functions must be the same. Sine, theta. Now we have to look at this internal sign. I see a positive, minus, minus, and 2 positives. So we're going really cycling between 2 minuses, 2 positive, 2 minuses. But again, whatever you see in your 5th round will mirror your 35th round in terms of everything. Theta, cosine, theta. And that right there would be your outcome, your end result. You could actually do more with this question we want, but think about it in your head, you could. What you can do is once you've determined the pattern, you can basically determine any number of derivative for this. You know you're always increasing by 1, and you know the signs for this initial part right here is always 2 positives, 2 minus, 2 positives, and you know you're always looking here in terms of the internal signs, 2 minuses, 2 positives, 2 minuses, 2 positives, and then this last terminal function always alternates. It's cosine, sine, cosine, sine, cosine, and then sine. Look at this initial function, it also alternates by 1. Sine, cosine, sine, cosine, sine. If you know this is 1, this is 2, this is 3, this is 4, 5, and then you know this is always your, going by 5, this always is your 10th, your 15th, your 20th, your 25th. You could easily determine what the 19th would be. Think about it. If this is 5, this is 10, this is 15, then this is 16, 17, 18, 19. The 19th order derivative will mirror what you have as your 4th order derivative. You just have to put a coefficient of 19. It would be a minus 19 cosine theta plus theta sine theta. Exactly everything as you see it as your 4th. The only difference here is you're changing the coefficient from minus 4 to a minus 19, because that ends up being your 19th step as well. The 4th ends up being your 19th, and the 4th will always end up being your 29th step. If this is the 25th step, then 26, 27, 28, 29th. Again, you can see how the pattern plays out, but it's good for you. It's good for me, and I'm happy with this answer. My answer, I'm putting it right here on the top, is 35 sine theta plus theta cosine theta, and that's your 35th order derivative for that function presented over there. And this right here is this video completed. Thank you for watching. Have a nice day.